Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and we're in the unbiased phase of the hypothesis testing playlist. Now, we're looking at two-sided, uniformly most powerful, unbiased tests, and in previous videos we looked at simple versus composite hypotheses, and the next few videos we're going to look at composite versus composite hypothesis in the same setting, two-sided, uniformly most powerful unbiased test. Now in this video we didn't prove a theorem, we stated a theorem, and that's what we're using in these videos. Now at the end of several examples and our illustrations, we're going to go back and prove that theorem for these tests, but I'm giving lots and lots of examples. So this one we're going to look at the normal mean. And the example is our data is normally distributed with mean mu and variance sigma squared. We're going to take a sample size n. For this test, we're going to assume that sigma squared is known. We're going to test at the alpha level. And the test is that the mean is somewhere between mu1 and mu2 versus the alternative hypothesis that it's either less than mu1 or greater than mu2. Now, the normal distribution density looks like this right here, and we can transform it into the exponential form. So we multiply this quadratic out and separate, and that's what this is. So this is a function of the unknown parameter mu. Remember, we're assuming we know sigma squared, and then this is a function of mu and our data, x, and then this is just a function of the x's. And the theorem says that this piece here is our test statistic. And then since we're taking a sample size n, we sum it, so it's the sum of the TIs, which then we sum this, so it's 1 divided by sigma squared times the sum of the xi. But if we multiply by n, divide by n, we can just call it x bar. Then the UMPU, which is unbiased, test is given by this test function, phi. It's a 1, meaning we reject the null hypothesis, is if our test statistic is strictly less than C1 or equal to, or is it less than or greater than or equal to C2. And we do not reject, meaning 0, if our test statistic is between these two values. Now what we are going to do is use an equivalent test. So if we divide everything by the same constant, it actually doesn't change the probabilities, and the tests are 100% equivalent. So what we're going to do is multiply everything by sigma squared and divide by n, right? So then here it leaves x bar, and then here we get just some, I'm going to call it C1 prime, it's some constant. We get C2 prime, C1 prime, C2 prime. And then this is the test that we're going to derive. Now C1 prime, C2 prime are determined by these two equations. It looks like one, but it's really two. The first one is that the expected value of the test function, assuming that mu1 is the true value, right, is alpha. And then the second equation is that the expected value of the test function, assuming that mu2 is the correct value, is alpha. So now if we look at these, the first one, the first equation, alpha is equal to the expected value of the test function, assuming that mu1 is the correct value. Since phi is a discrete value, it's the value times the probability of it happening, so it's 0 times that, and 1 times the probability of this happening, which is what these two pieces represent. That, or in this case, this. So the probability that x bar is less than C1 prime, plus the probability that x bar is greater than or equal to C2 prime, assuming mu1 is the true value. Now if we subtract the mean, mu1, divided by the standard deviation, then it transforms it to a Z random variable, standard normal. So that's what this is, right? Now you can generically call this, C2 prime, double prime, and this C1 double prime. And you can use these to solve the equation, then kind of back solve for C1 and C2 prime. But we'll use these equations. Now the second equation is that mu is equal to the expected value of the test function, assuming mu2 is the correct value, which are these, probably x bar is less than C1 prime, given that mu2 is the correct value, and the same way here, x bar is greater than or equal to C2 prime, given mu2. And then of course you can subtract mu2 divided by the standard deviation, transform it here. So let's draw a picture of what we've done so far. Now, if mu1 is the true mean, that means our normal distribution looks like this. And then the C1 prime is some value less than that. If mu2 is the true mean, then it's this, and then this is C2 prime over here. But notice that the variances associated with these normal distributions is the same. So this area here is equal to this area here. So we set them equal, right? Assuming mu1 is true, mu2 is true, then these probabilities. Now if we transform this to a z random variable, subtract the mean divided by the standard deviation, we get this. And then do the same way here, subtract mu2 divided by the standard deviation, sigma over square root of n. Then well, it's not this value, but the transformed value are negative of each other. So this is equal to the negative of that, right? So when we bring this down, it's going to be a positive value in the z curve. And when we bring this down, it's going to be a negative value in the c curve. So if we set this equal to the negative of that, then we can solve for C2 prime. Then we can plug that back into here and solve for C1, okay? And that's what we do. We plug this, instead of being C2, we put in what it equals. Now, if we subtract the mean, mu1 from both sides, divide by the standard deviation, we get this. Now look at this, mu is equal to this. And there's only one unknown, C1 prime, right? So this is easy to solve, and we'll use uniroot in R to solve this, and it's instantaneously. But the way you do it is you pick a C1 prime and then calculate these two probabilities, right? It's only unknown. And if it's above or below alpha, then you either increase or decrease C1 prime, and you just do that iterative process to its alpha. And then you solve for C1 prime. And then you can take it and back solve for C2, right? Because it's this value. Okay. Now, the next test I'm going to show you is not in books. I've never actually seen it. The only place I've seen it is calculating sample size, for experiments. If it's a two-tail test, some softwares do this. So, and it's basically leave out one tail. So if mu1 or something smaller is the true value, then the curve looks like this. But the probability that we see a value greater than C2 prime is pretty small, especially if mu1 keeps getting smaller. So if we leave this tail out to calculate this, it's actually pretty darn close. So we just choose that to be alpha, or alpha. And then the same way too, if the true mean is mu2 or bigger, then the probability that we're less than C1 prime is really small. So we just leave it out. And again, this is a test I made up. It's based upon what I've seen some sample size softwares do in calculating for the mean. So I'm going to call this leave out one tail test. And again, this is, I've never seen it in books, but to me it seems like a pretty reasonable thing to do because it's so easy to find C1 prime and C2 prime. Now, of course, with today's computers, why wouldn't you always do the uniformly most powerful unbiased test? But this is so easy to solve for C1 and C2. So here's the test. Alpha is equal to this, so it's the probability that x bar is less than C1. Subtract the mean, mu1, divide by standard deviation, we get this. We want this to be 0.05, or alpha. And so this has to be z sub alpha. And then you set this equal to z sub alpha and solve for C1 prime, you get this. And then over here, probably x bar is greater than C2, assuming mu2 is the correct value. Transform it to a z, then this has to be Z sub 1 minus alpha. That means the right tail is alpha. Set it equal to that, solve for C2 prime, and you get this. Now, in the R illustration, we'll do both of these tests, and I'll show you that they're really, really close to each other. Now, the example we're going to do, if you want to kind of fiddle with this before the next video, which is an R illustration, is that we assume our data is normally distributed with some mean and known variance of 9, alpha's 0.05. We take a sample size of 22. The null hypothesis is that mu is between 7 and 8. The alternative is that it's either less than 7 or greater than 8, right? And that's a composite versus composite hypothesis. The uniformly most powerful unbiased test is given when C1 prime is this and C2 prime is this. The leave out one side is C1 prime is this, which is pretty close, right? And C2 prime is this. Now the this C1 prime and this C2 prime actually approaches these values the further and further the null hypothesis values get. But that's a side topic. So in the power curves are essentially right on top of each other. A little gap, so you lose some power. And that's it. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.